So we talked a lot about light and about waves and particles. Now we're going to bring that into chemistry. So when atoms or molecules absorb energy, that energy is often released as light energy. And it looks like there's something missing there. There's a comma and nothing after it. I don't know. Examples of this in real life are fireworks, neon lights. Here we have 3 discharge tubes, mercury, helium, and hydrogen lamps. And these are glowing. They're evacuated tubes filled with elements in their gas states. And then we pass an electric current through here. And so the mercury absorbs energy, and then it has to release that energy again, and it gives off this blue light. Helium gives off kind of this pinkish purple light, and hydrogen gives off more of a reddish light. This is what? A neon sign. And that has actually got neon in it. It's basically a tube like this, but they bend the glass around and make it into a shape that says something. That bright orange color is from the element neon. They do make other colored lights, but those do not contain just neon. Well, when light that is emitted from one of these lamps passes through a prism, instead of seeing a rainbow like we do with sunlight, we see a pattern of particular colors. Remember, the color and the wavelength are related. This is called an emission spectrum. So it's not continuous. It has bright lines and mostly dark in between. It can be used to identify the element. It's a lot like a fingerprint or a barcode that you might scan at the grocery store. It's a series of lines, and their specific pattern is unique to that element. This phenomenon cannot be explained by classical physics. So here's what's going on here. So here we have a hydrogen lamp, and we pass that light through a slit and through a prism. The prism separates it into component wavelengths, and we have 3 lines, 4 lines. The one on the end is really hard to see because it's almost ultraviolet. Normally you'd see from a light, like an incandescent light bulb, or from the sun you'd see a continuous rainbow, but we just get these stripes. So this is what helium looks like, this is what barium looks like. And so they're very different. They kind of look like barcodes. This is what sunlight would look like. And this is oxygen and neon. You see some of them are quite complicated. There's a lot of different lines. Any questions about that?
So why do we have rainbow?
Pardon me?
Why do we have rainbow?
Why do we have a rainbow? Because the light from the sun contains light of every wavelength. Because it's coming, that's really kind of a complicated thing of why is it continuous, but there's lots of different emissions going on, not just from a single element.
Like, what is the prism?
So a prism is usually a piece of quartz or glass, but sometimes plastic, and it just separates the wavelengths of light.
I mean, what is the prism for the white light to appear as the rainbow?
The same prism. So this same prism, if you shine sunlight through it, you'll see a continuous rainbow. So the light coming off of this hydrogen lamp contains visible light with only 4 specific wavelengths. So that was actually a really good question you asked, because it's a little hard to understand. Why would it do that, right? It has nothing to do with the prism. It has everything to do with the source of the light. So we can look at emission spectra. We can also look at absorption spectra. You can shine light on an element in the gas state and get it to absorb light and look at what light passes through. And then you see, this would be the emission spectra where you get bright lights, bright lines, and this would be the absorption spectrum where you get dark lines. So it's absorbing the light the same place that it would emit the light if it was the opposite. Yeah, this isn't going well. It's okay. We'll muddle through somehow. A very low-tech way of identifying elements is a flame test. And so you take an inert wire and you dip it in a solution of sodium and you heat it up and you get this bright orange-yellow color. That is characteristic of sodium. With potassium, you get this lovely lavender-colored flame. Lithium gives this intense red, and barium kind of has a greenish color to it. The color that we are seeing in these flames is the combination of those individual lines that are being emitted. And so the color depends on the specific combination of lines. So Johannes Rydberg looked at these atomic spectra, because when scientists first observed these, it was very puzzling. Like, what's going on here? Why is this happening? Why does it only give these specific lines? So Rydberg looked at lots of different atomic spectra and came up with an equation that predicts what the wavelengths are with integers. And so 1 over the wavelength is equal to a constant times 1 over m squared minus 1 over n squared, where m and n are just constants. They're integers. So this is nice, but it's not really that helpful, right? It doesn't explain anything. It just says, okay, well, we could predict where the lines are. Awesome. We didn't really want to do that, but whatever. Doesn't explain why the atomic spectra are discrete, individual lines. Doesn't explain why atoms are stable. Doesn't even explain why the equation works. Just, okay, we've got an equation to describe what's going on. So let's revisit Rutherford's nuclear model of the atom. The atom has a tiny dense center called the nucleus. In that nucleus is essentially all the mass of the atom. The nucleus is positively charged. The amount of positive charge balances the negative charge in the electrons, and the electrons are doing something in that empty space, which constitutes most of the volume of the atom. So Rutherford's model, was an advancement, but it's got some issues too. So these are some of the problems. Electrons are moving charged particles. And according to classical physics, a moving charged particle gives off energy. So then the electrons should be constantly giving off energy. And if that's the case, you would expect that the atoms should glow, but they don't. If they're giving off energy and energy is conserved, they must eventually run out of energy, crash into the nucleus, and the atom should collapse. But it doesn't. So the nuclear model doesn't explain what structural changes are occurring when this emission of light happens, and it's got these other issues with the charged particles. So obviously there was a need for some improvements. So Niels Bohr developed a model of the atom that explained what's going on with the emission spectra. So in his model, electrons travel around the nucleus in circular orbits, and this is a lot like a planetary system where you have a sun and you have planets orbiting the sun. We're all familiar with that. The nucleus is like the sun and the electrons are like the planets. Okay? The orbits for those electrons exist only at specific fixed distances. So there's only certain orbits that they can be in. The energy of those orbits is fixed or quantized. There are specific levels. And the amount of the energy in the atom is related to the electron's position in the atom. So this word quantized is important. Quantized means the atom can only have very specific amounts of energy. So we have examples of quantized and continuous things in real life. So if you think about going up a set of stairs, you can stand on the ground, you can stand on the first step, the second step, or the third step. You can't stand in between two steps, right? So there are particular levels. You can be on the first step or the second step, you can't be in between. But if you have a ramp, you could scooch up just a smidge or a little bit more. You could be anywhere along the ramp. So in terms of elevation above the ground, the stairs are quantized, the ramp is continuous. There are examples of this in musical instruments. A guitar is quantized, a violin is continuous. On a guitar, there are frets, and you put your finger on the string touches the fret, that's the note. It doesn't matter exactly where your finger is. On a violin, it does matter because there are no frets. And if you've got your finger in just slightly the wrong position, the note's not quite right, and that's why you can make such horrible sounds on a violin. I know because I took violin when I was a kid. I should have called my mom and apologized to her later. Okay, our monetary system is quantized. Think of bills, right? $1 bill, the lesser known $2 bill, 5, 10, 20, 50. There's no $17.53 bill, right? Doesn't exist. You can't have one, okay? So that's quantized versus continuous. So the electrons in this model are quantized in their energy. So here's a diagram. There's the nucleus, and we've got the electrons. Here's the first orbit and the second orbit, the third, the fourth, the fifth. As you move away from the nucleus, the energy increases. The electrons have to be in one of the orbits. They can move between them, but they do so instantaneously. So when they move from a higher energy orbit to a lower energy orbit, that energy has to go somewhere, and it is emitted as a photon of light that has a particular energy and thus a particular wavelength. So we see for the hydrogen atom that when an electron makes a transition from the fifth orbit down to the second orbit, it releases a photon of light that has a wavelength of 434 nanometers, and we perceive that as a violet line on the spectrum. For the blue-green one at 486 nanometers, that happens when an electron moves from 4 to 2. Red is from 3 to 2. There are other transitions, but the energies of those transitions are outside of the visible spectrum, and so we can't see them with our eyes. So we only see really these three. Any questions about that? So the electron is never observed between states. It is only in one state or another. It's called a quantum leap. It's in one level, and then bang, it's in another level without going through the space in between. That seems impossible, doesn't it? Well, the electron belongs to that category of the absolutely small. It doesn't have to behave like normal objects do. So the energy of the photon that gets released is the difference in energy between the two states. How does it get to a higher energy? It absorbs energy from something around it. So we can calculate the energies of those orbits from the wavelengths of the spectral lines. And this was really awesome. The problem is, it only works for hydrogen. It doesn't work for anything else. So that was kind of a bummer. So the Bohr model is not correct, but it is historically important. It's conceptually important. And I give you permission to kind of visualize the atom in this way because it's easier to think about than the true quantum mechanical model. So any question about the Bohr model of the atom?